Hey gang, although I've experimented with the LM386 for 3 decades, I've never built a discrete transistor version until now. I learned a ton and I'm going to share it with you. I hope that after watching this video, you'll understand how the LM386 differs from typical Class AB audio power amp ICs. As well, you'll know exactly how it works. Further, we'll compare my homebrew LM386 to a real deal Texas Instruments LM386 N chip, and I hope you'll pick up some tips and tricks along the way to enhance your own bench experiments. A little bit of history. In the photo lies 2 LM386 N-1s. These are National Semiconductor parts from my collection, and these were built in 2006. The legendary National Semiconductor team added the 386 to their LM series in 1983. They offered 3 versions. The current is the N-4 variant. And note that Texas Instruments purchased National Semiconductor in 2011. Globally, the LM386 was also licensed to JRC, Nintendo Micro, and Unisonic Technologies. Happily, the LM386 is still available in DIP package for us older, visually challenged builders. Here I'm just going to go on Mouser, find the part through their search engine, and then open the data sheet. I've got the data sheets for all 5 companies that built the 386. They're all the same, so you might as well just go get the latest one from Texas Instruments. On your screen lies an experimental, single supply, low power audio power amp. Please focus on the input, Q1 and Q2, which are a differential pair. However, I prefer to say emitter-coupled pair. Looking at the top 12-volt DC positive rail, we see that it terminates in a 27K voltage divider on the far left. Since R1 and R2 are the same value, we know from Ohm's law the voltage divider will divide the 12 volts in half to 6 volts. Moving down vertically, we have a 220 microfarad capacitor to low-pass filter and stabilize the 6-volt bias voltage, and it's connected to the base of Q1 via a 10K resistor R3. If R3 were not a high resistance value such as 10K, an AC input signal on the input could flow through R3 directly through the 220 microfarad capacitor to ground. Instead, with R3 at 10K, it flows into the base of Q1. Let's focus on the base bias of Q2. If you refer to the point X, which is the output rail of the amplifier, it too will be at approximately 6 volts DC. Moving left from point X, we go through a 15K series resistor onto the base of Q2, so the base bias of Q2 is also approximately 6 volts. The 15K and 270 ohm resistor help determine the voltage gain of the power amplifier. If the 220 microfarad capacitor was not between them, they would actually form a DC voltage divider, and Q2 would not receive around 6 volts DC bias. The 15K 270 ohm plus 220 microfarad capacitor form a negative feedback network connecting the output, which is point X, to the input, which is the base of Q2. So we have the output of the amplifier getting negative feedback to the input of the amplifier through the base of Q2. In summary, for the Q1, Q2 emitter coupled pair, each of the bases of the transistors gets approximately 6 volts DC bias. Q1 receives the audio signal input, and Q2 receives the negative feedback from the output. This is typical for most integrated circuit Class AB audio power amps. In fact, it's how most op amps work as well. Okay gang, this is the LM386 datasheet schematic with the pins shown in blue. Did you notice the two main differences between this and the previous schematic? If you thought, well, there's no direct DC bias to the input pair and that the negative feedback goes from the output to the input pair emitters, you were correct. Before we take a deep dive into the actual bench schematic, please view the resistor between pins 1 and 8. Here's my bench schematic. Note that I eliminated pins 1 and 8 and fixed the voltage gain with a 1K resistor, and the voltage gain equals 61. Let's focus on the input stage. The input emitter coupled pair are Q7 and Q8. Q6 and Q11 are emitter followers, and their bases are voltage reference to ground via 47K resistors. These resistors set the input impedance of the LM386 device. The Q6 and Q11 emitter followers serve as level shifters and allow incredible sensitivity, which is something you would need when you're operating a device with a voltage gain of 200. That works out to 46 dB gain, which is a heck of a lot of gain for any audio stage, let alone an audio power amplifier. The voltage gain of the LM386 can be set between 20 and 200, which is 26 and 46 decibels. Right, let's discuss Q9 and Q10, which provide the collector load for the emitter coupled pair. In my opinion, Q9 and Q10 are the heart of the LM386 and allow the output rail to lie at half of the set DC voltage, plus facilitates the impressive clean output power swing that we enjoy with the LM386. Typically, as a radio builder, I would use a resistor for a collector load at audio frequencies. In linear ICs, rather than load resistors, often enough, active loads, which are termed current mirrors, get used instead. The current mirror supplies the collector load and load biasing elements, plus gives a single-ended output drive for Q3, which is the main signal voltage amplifier. So in summary, Q9 and Q10 form a current mirror. In a real LM386, Q9 and Q10 and all of the other transistors are fabricated on the same die. Thus, the emitter-coupled pair, Q7 and Q8, plus the two current mirror transistors are matched and enjoy the same transistor base to emitter voltage and current gain. Also, they track thermally. In normal operation, each half of the current mirror is perfectly balanced, hence the name current mirror. Q7 and Q9 conduct half of the current, while Q8 and Q10 conduct the other half. The entire input stage functions as a current amplifier. Essentially, the input stage subtracts the negative feedback signal from the input signal, and the voltage difference between the input and the negative feedback arm results in an output current to drive Q3. Let's focus on the parts between and including Q1 to Q3. I call this the driver stack. Q1 is a very basic PNP current source. A convenient way to change the output current is to vary R1. I tabled 3 different R1 values versus current. Pushing more current in this stack raises the quiescent current through the finals. I settled on 22 ohms to keep from heating up the finals too much during my maximum clean power testing. Again, Q3 functions as the voltage amp. This is where the voltage gain in the LM386 happens. In between Q1 and Q3 lie two diodes. These diodes establish the differential bias for the finals, meaning that they slightly forward bias the push-pull output transistors Q2 and the complementary feedback pairing of Q4 and Q5. Now, let's imagine if the diodes were not present, that the transistors were not forward biased slightly. Each final transistor will not turn on until the appropriate polarity AC waveform forward biases the transistor by about 0.7 volts. A positive going AC signal for an NPN transistor and a negative going signal for a PNP. Please think of the Q4-Q5 pairing as a PNP transistor for now. On your screen, this is what it looks like at the output rail in time domain, since each final transistor only turns on when the AC signal goes about 0.7 volts, positive or negative. In effect, a dead crossing zone exists. This is called crossover distortion. It sounds terrible. Crossover distortion also looks terrible. Here we are in frequency domain and FFT. These are odd order harmonics. You're actually viewing harmonics 3 and 5. In this slide, I add back the two diodes, which greatly reduces the crossover distortion. Forward biasing the finals with the two diodes means that even a slightly positive or negative input signal will cause the push-pull finals to conduct on alternate cycles of their AC input waveform. Okay, gang, we need to talk about the LM386 finals. The goal of a power amplifier is to swing the largest clean output signal between the DC power supply rails as possible. In my case, the rails lie between 0 and 12.3 volts DC. Here's the million-dollar question. Why didn't the 386 design team just go with a pair of emitter followers for the finals? I show this in the current slide as experiment 2. Well, the main problem is that the LM386 design is limited to a low voltage single DC supply. Within this limitation, in order to get a power amp output signal swinging as close to the DC rails as possible, you must depart from the bog standard complementary pair of emitter followers. Why, you may ask? In the classic pair of emitter followers, the collector to emitter saturation voltage plus VBE keep you from getting close to the rails. So in most audio amp ICs, you'll see the finals configured other than as a complementary pair of emitter followers. I completed experiment 2. My clean output power swing into a resistor load was only about 75 to 80% of what I got with the normal LM386 output circuit, despite manipulating the negative feedback circuit to help balance my output swing. In the 386, they keep the NPN emitter follower Q2, but in the PNP slot, they employ a wraparound feedback pair consisting of a PNP plus an NPN transistor. This configuration is called a complementary feedback pair. This pair behaves like a single transistor but offers greater current gain. The current gain is the product of the current gains of the two transistors, and some people call this a beta multiplier effect. In some cases, for the PNP transistor slot, you might see a 100 to 220 ohm resistor shunt to ground in some single supply audio power amps. This helps the transistor switch off quicker at higher frequencies. In the LM386, they omitted this resistor. Complementary feedback pairs seem really cool, and if you depart from the one-to-one feedback as used in the LM386, you may configure them to give voltage gain. This offers more output swing from the same DC rails. You're viewing an experimental power amp from December 2025. I used a rail-to-rail op-amp as the driver and employed two complementary feedback pairs with a voltage gain of a little over 1.1. I was able to drive this amp to around 10 volts peak to peak, or 1.63 watts, with only 15 milliamps of quiescent current. This is not possible with an LM386. It's feedback circuit time. All components colored black are part of the feedback circuit or help maintain proper operation as you change the voltage gain, and to a point if you add additional negative feedback to shape frequency response by placing an external RC network between output pin 5 and pin 1. For voltage gain management, if the junction between pins 1 and 8 are left open, the voltage gain is minimum or 20. If you fully bypass the resistor between pins 1 and 8 with an audio capacitor, the voltage gain approaches 200. If you partially bypass the pin and 1/8 junction with a resistor and capacitor in series, you can dial in a gain between 20 and 200. The datasheet covers this well, and I won't linger. For LM386 noise management, this part is a bit noisy. The input noise density is about 50 nanovolts per square root hertz. Choosing a higher voltage gain on the LM386 means that you are building up your audio stage voltage gain with a noisy part. You may not care about that. If you do care about noise, it's better to build up your voltage gain with low noise op-amp stages such as the NE5532 and use a lower voltage gain setting on the LM386. Finally, from careful bench experiments and SPICE-based analysis, C1 should not be less than 100 microfarads to get proper low-frequency bandwidth and to reduce harmonic distortion somewhat. Life is too short for 100 microfarad audio bypass caps, so my audio capacitor collection starts at 220 microfarads. Comparison time. Let's start with the real LM386N-4. One of the greatest determinants of amp headroom or the clean voltage swing is the DC supply voltage. My comparisons were completed with the same DC power supply at 12.3 volts. The LM386 seems a nuanced device. You may change voltage gain, add additional negative feedback, and DC or AC couple the input signal. Further, you may terminate the unused input by connecting the unused input to ground via a wire or a small capacitor, or even leave it open circuit, although leaving it open circuit is not recommended. According to the figure shown, I AC coupled the input signal. Pin 2 is AC coupled to ground. My signal capacitors were metal film type since electrolytic caps may add distortion. I adjusted a 5K trim pot until I measured a voltage gain of 61. I'll show some FFT slides of the LM386N-4 driven to 5 and then 7 volts peak to peak, and then compare the results to FFTs of my home-built 386 clone. The often quoted percentage of total harmonic distortion does not make much sense to average hobbyists. I prefer to look at the harmonics expressed as decibels down from the carrier or fundamental. When driven to 5 volts peak to peak or 411 milliwatts output power, the worst harmonic is minus 52 dBc. This is quite acceptable for a transistor radio. Remember minus 52 dB down as we move to about 7 volts peak to peak, or 812 milliwatts output power. The harmonics are now less than or equal to minus 48 dBc. This still seems okay. Yikes, gang! Look what happens when we drive the LM386N-4 to 7.39 volts peak to peak. The third harmonic is only 28 dB down from the fundamental. We are squaring up and entering compression. Some might call this 898 milliwatts of output power, but that seems like inaccurate storytelling. Let's show a couple of bonus slides. We are back to 5 volts peak to peak again. This time I put an audio cap between pins 1 and 8 of the LM386 to give a voltage gain of 200. Recall that the second harmonic was minus 52 dBc for a voltage gain of 61. Now, with a voltage gain of 200, the second harmonic is 5 dB worse. Increasing the voltage gain to 200 worsens headroom and also potentially increases noise, as discussed earlier. In this FFT, the LM386 is driven to 7 volts peak to peak. I removed the cap between pins 1 and 8 to get a voltage gain of 20. In the earlier 7 volt peak to peak slide with a set voltage gain of 61, the third harmonic was only minus 48 dBc. Now it's 53 dB down. Choosing the low gain mode both lowers harmonic distortion, but also noise if you choose to build up your AC signal voltage with low noise op amps. Here lies the FFT of my discrete transistor 386 driven to 4 volts peak to peak, or 263 milliwatts. Sadly, above 4 volts peak to peak, the harmonic distortion starts to really take off. When driven to 5 volts peak to peak, I'm unable to make a reasonably clean signal. In short, my discrete transistor 386 sucks lemons compared to a real deal LM386N-4 IC. For fun, let's look at a time domain DSO shot of my 386 driven to its maximal clean output power, 332 milliwatts. That's about 41% of the clean signal output power of a real LM386N-4. Bummer. Final FFT. Here's the FFT with the amp driven to 4.9 volts peak to peak, or 395 milliwatts. Pathetic plus poor headroom in this audio power amp. So why did my discrete transistor 386 clone suck when compared to the real deal LM386N-4? One big factor might be that my project was not made on a single die. There was no matching of BJT current gain or VBE, and for sure there was no thermal tracking. I probed my circuit with a frozen plastic probe and a hot plastic probe by touching transistors. Any temperature change on any transistor upset the output signal. My amplifier seemed extremely temperature sensitive. When I breadboarded the circuit, I did not match the emitter-coupled pair nor the current mirror transistors. Further, I probably should have added emitter degeneration resistors to the emitters of Q9 and Q10 to boost current matching in the current mirror. I didn't really want to deviate from the LM386 circuit too much, but normally I would do this in a homebrew current mirror for an amplifier. Continuing on, another thing I thought about is IC manufacturers may fabricate specialized transistors on a die. For example, higher beta final transistors. What is the difference between the LM386 variant 1, 3, and 4? The schematics all look the same, so it's a good question. What did they actually do on the die to the transistors? Further, using T092 small signal transistors as audio power finals is probably foolish. These transistors were designed for small signal work. Certainly you can use them as power amps, but it is possible that some small signal transistors, when you start putting the collector current above 10-20 milliamps, their beta starts to drop or droop. Likely, for the finals, I probably should have employed medium audio power transistors, such as the BD139-140, or a tip transistor such as the 31C, 32C. In the December 2025 1.63 watt amplifier I showed earlier, I employed the BD139 and 140, and they worked quite well. They're also easier to heatsink. Although the amplifier performance kind of sucked, I'm actually quite happy with the outcome. I learned a ton, and I define success as whenever I've learned something. Digging through some old files, I found my very first LM386 experiments from 35 years ago. Back then, I was using my old tube Tektronix scope with the beautiful CRT display. And I was looking at the LM386-1, and if you look at my results then, I actually replicated them. So compared to an LM386N-1, my home-built discrete transistor LM386 clone, it doesn't quite suck as bad as I thought. Well, we've come to the end, and I just want to say a big thanks to my mentors, Ken Kuhn and Wes, W7ZOI, for answering all the millions of questions I've asked them over the years. And I also want to thank you, the viewer, for watching until the end. Take care. Bye-bye.